All right, let's jump right into today's explainer. Now, when most of us think about the Maldives or the Lakshadweep Islands, our minds immediately go straight to those pristine white sand beaches, crystal clear turquoise water, peaceful coral reefs, basically a tropical paradise, right? But what if I told you that hiding directly beneath these tranquil island getaways is a massive, violent geological mystery? We're talking a tectonic story filled with tearing continents, massive volcanic eruptions, and a sunken landmass that's actually suffering from a literal underwater identity crisis. So today we are going to peel back the ocean waves and those coral reefs to uncover the true geology of the Lakshadweep Ridge.
Okay, so let's get our bearings. If you point your eyes toward the western coast of India, extending southward from roughly 14 degrees north latitude, all the way down past the equator to about 6 degrees south, you'll find the Chagos Lakshadweep Ridge system. We're specifically focusing on its northern segment, the Lakshadweep Ridge. This thing is huge. It's a massive, unbroken submarine mountain range stretching for about 2,500 kilometers right across the Indian Ocean. And for decades, this giant bathymetric high has just stood out on our seafloor maps as this towering, unexplained underwater plateau.
Which naturally brings us to a really big question, and honestly, the very heart of today's explainer. What exactly lies beneath those pristine coral atolls? You see, a coral reef is, at the end of the day, just a biological cap. It's a really thin layer of life sitting on top of foundational rock. For the longest time, geologists looked at this immense underwater ridge, which extends 24 kilometers deep into the Earth's crust, and just scratched their heads. The structures down there, they just didn't make sense.
And that sheer confusion led to a central debate that absolutely baffled the scientific community for years. On one side of the ring, you had the Oceanic hotspot trace theory. This camp suggested the ridge was simply a trail of oceanic volcanoes. Just basaltic rocks piled up on normal ocean floor as the Earth's crust slowly moved over a stationary blowtorch of mantle magma. But on the other side, you had the Continental sliver theory. These folks argued that the ridge was actually a fragmented, sunken piece of an ancient continent that snapped off from India. So what's the verdict? Are we looking at a volcanic trail or a broken piece of a lost continent?
Well, to solve this geological detective story, we really need to trace a rapid-fire sequence of tectonic events. We'll kick things off 88 million years ago when India and Madagascar first separated. Then, we'll examine a crucial piece of evidence from about 76 to 78 million years ago. And finally, the climax of our story, the arrival of the massive Réunion plume between 66 and 60 million years ago. Let's start at the very beginning. So this brings us to clue 1. A continental sliver breaks free. Roughly 88 million years ago, back during the late Cretaceous period, the massive supercontinent of Gondwana was violently breaking apart. Just try to imagine the immense tectonic forces required to tear entirely intact landmasses away from each other. As India and Madagascar slowly separated, the western margin of what is now India was subjected to this severe, prolonged stretching.
Think of continental crust kind of like a thick piece of warm caramel. When you pull it apart, it doesn't usually snap cleanly in two, right? It stretches out, it thins, and it structurally weakens. And that is exactly what happened to the Darwar Craton, which is this massive block of ancient crust on India's western edge. The intense stretching created deep faults and thinned the crust to the point where a narrow, weakened ribbon of Precambrian rock completely broke off and got totally isolated from the Indian mainland. Geologists actually often refer to this ancient lost fragment as part of the Mauritius microcontinent.
Now, for a while, that whole continental sliver idea was just a neat theory, but the definitive proof came from deep-sea drilling at a location on the northern ridge called the Padua Bank. Drill cores brought up actual igneous basement rocks from deep beneath the seafloor sediments. Using argon-argon radiometric dating, which is incredibly precise stuff, scientists discovered these were rhyolite rocks dating back 76 to 78 million years. Here's why that's a game-changer. Rhyolites are highly acidic, silica-rich rocks. That is exactly the kind of rock you find in a continental crust undergoing rifting, not the typical basaltic rocks you'd expect from a standard oceanic mantle plume.
So, the crucial takeaway here is summarized perfectly by this quote from the source literature. The volcanism predates the Réunion plume volcanism, indicating a thinned continental crust. Why does this matter? Well, it means the Lakshadweep Ridge already existed as a thinned-out, rifted continental sliver long before any volcanic hotspot showed up. It actually had its own pre-existing structural identity. But of course, the story doesn't end there. Our already battered, severely thinned-out piece of continental crust was drifting steadily northward on the Indian plate. And waiting right in its path was one of the most powerful geological forces on Earth, the Réunion mantle plume. Talk about being in the wrong place at the wrong time, right? Between 66 and 60 million years ago, this massive upwelling of superheated mantle material, literally the very same blowtorch that created the vast Deccan traps in India, collided directly beneath our fragile little continental sliver. Now, when a massive plume hits a thick, strong, healthy continent, it might just punch a few volcanoes through to the surface. But remember, our Lakshadweep Ridge had been stretched like caramel and severely weakened. It physically couldn't support the massive upward pressure and volume of the magma. This resulted in a phenomenon called magmatic underplating. Instead of all the magma bursting onto the surface, enormous volumes of heavy, dense magmatic melt just pulled and cooled directly at the bottom boundary of the crust. To really wrap our heads around just how compromised this continental sliver was, consider this measurement: just 3 kilometers. This represents the Rogradish Ridge's effective elastic thickness. That's a fancy term geologists use to measure how much load a tectonic plate can support before it starts to bend. A normal continental plate might have an elastic thickness of tens of kilometers. A value of just 3 kilometers is astonishingly low. Imagine a lithosphere so incredibly weak and flexible that it was essentially acting like a paper-thin roof sitting right over a churning magma chamber.
Okay, so what exactly happens when you take an ancient, stretched-out continental sliver and violently inject its basement with millions of tons of high-density hotspot magma? Well, you get a structure unlike almost anything else on Earth. Let's virtually slice the modern ridge open, side on, and look at the anatomy of this crazy geological layer cake.
Peeling back this bizarre hybrid structure, we start with a thin layer of modern sediments and coral carbonates at the very top, that 0 to 3 kilometer range. Just beneath that, there is a 3-kilometer thick cap of flood basalts. Those are the surface eruptions left over from the Réunion plume. But the real shocker? That's sandwiched right in the middle. From 6 to 11 kilometers deep, we find seismic velocities perfectly matching thinned Precambrian continental crust. The ancient ghost of Gondwana is literally right there. And finally, supporting the whole shebang, from 11 to roughly 25 kilometers deep, is that massive, heavy, high-density underplated root of magma we just talked about. Which leads us to an absolutely astonishing depth of 24 kilometers. That is where the moho, which is the boundary between the Earth's crust and the mantle, is located right beneath the Lakshadweep Ridge. Just to put that into perspective for you, normal oceanic crust nearby is only about 6 to 7 kilometers thick. Having a 24-kilometer crustal thickness proves definitively, without a doubt, that this is not just some normal oceanic hotspot trace. It is a thick, highly modified continental block.
But there's a catch. This heavy, magmatic underplating created a serious long-term problem for our ridge. As you trace the path of the Indian plate moving rapidly northward, our heavy, magma-loaded ridge eventually moved off the hotspot's heat source. And what happens to dense, underplated rock when it finally cools down? It becomes even denser, and it inevitably begins to sink.
And that brings us to the final stages: migration, subsidence, and colonization, which built the tropical world we recognize today. As the thinned continental sliver, heavily burdened by its dense magmatic underplating, migrated away from the hotspot, it underwent severe thermal cooling and subsidence. The entire ridge began to slowly sink back into the ocean. Those massive subaerial volcanoes that once towered above the water were dragged slowly beneath the waves. But life found a way, right? As the peaks sank, shallow water reef-building corals aggressively colonized them. As the ridge subsided, literally just millimeters per year, the corals grew upward at the exact same pace just to stay in the sunlight. Over millions and millions of years, they built the massive, thick carbonate atolls that form the Lakshadweep and Maldives Islands today.
So, the Lakshadweep Ridge isn't just a simple trail of oceanic volcanoes. It's a lost, sunken piece of an ancient supercontinent, stretched to its absolute breaking point, injected with a massive mantle blowtorch, and then slowly dragged down into the abyss, only to be capped by a beautiful crown of coral. It just brilliantly illustrates the incredible, dynamic power of our planet. And honestly, it leaves us with a truly provocative thought. If an entire microcontinent can be stretched, roasted, and perfectly hidden beneath a tropical paradise, what other ancient continental fragments are lying silently beneath the world's oceans, just waiting to be discovered? Thank you so much for joining me on today's Explainer. Keep questioning the ground beneath your feet, and I'll see you next time.